Here is our next question in computer organization from the topic cache and main memory, which we are going to attempt. Question is, if the associativity of a processor is doubled while keeping capacity and block size unchanged, which one of the following is guaranteed to be not affected? This was asked in 2014 in set 2 for 2 marks. 4 options are given. So we need to determine associativity of a processor does not affect which one of the following: width of tag comparator, width of set index decoder, width of way selection multiplexer, width of processor to main memory data bus. So these are the 4 options, and here we can see that these are the hardwares involved in n-way set associative cache. So here associativity of a processor also means the value of n in n-way set associative cache. It is same as the value of n, associativity is same as the value of n in n-way set associative cache. So here value of n is associativity, and now we need to determine whether the change in value of n anyway affects any of these 4 or not. The one which is not getting affected would be the answer, right? So we need to determine which one is not getting affected. So here there are hardwares, those are mentioned: tag comparator, set index decoder, selection multiplexer, and main memory database. And we need to have a clear picture of where this hardwares fit into the determination of whether the data that has the CPU address that has generated by the CPU resides, the data of that CPU address resides in the set associative cache or not. So these hardwares are involved in that, in the determination process, and we need to have a clear picture of that. So let us start with identifying the fields of a CPU address in case of n-way set associative cache. So if it is CPU address, this is represented by this rectangle, so it can be divided into 3 fields. First set of fields is known as block offset, and let us designate the width of this block offset with small b. Next set of bits is known as set index. Let us designate it with small s, and the remaining fields are known as tag bits. Let us designate it with small t, and let the width of the CPU address be designated with small a. Now width of the block offset is given by this formula. Small b is log base 2 size of the block. So if say the size of the block, if the block contains say 4 bytes in a hypothetical computer, then a small b equals 2 would be equals to log base 2 4, that is equals to 2. So if there are 4 bytes in a block, the block offset would be 2 bits wide. Now the small s, that is the width of the set index, is given by log base 2 number of sets in the cache, and the width of tag field is given by small t equals to a minus out of, if we subtract the value of small s and small b from the value of a, then we would get the value of small t, a minus small s minus b. So the width of the tag field is the remaining bits. If we take out the block offset bits and the set index fields bits out of the CPU address, then what we are remaining is known as tag field. So the small t is equals to a minus s minus b. Now let us assume that we have a 2-way set associative cache. That means the value of n here is equals to 2, or in other words, associativity of the cache is equals to 2. So we have, for example, a two-way set associative cache. That means that each set of the block contains two blocks. Each set of the cache contains two blocks. And also let us assume that there are 32 blocks in all in the cache. So if there are 32 blocks and there are 2 blocks per set, then the number of sets would be equals to 32 divided by 2, that is 16. So if there are 32 blocks and it is two-way set associative cache, the number of sets in the cache would be equals to 16, that is number of blocks, total number of blocks divided by n. So there would be 16 sets, and let us represent the sets by these rows. Assume that the rows represent a set. Now this is two-way set associative cache, right? So each set contains 2 blocks, and also in cache along with set we also maintain metadata, right? Each block contains associated metadata. So first let us divide this cache into 2 parts. One would be the data part in which the blocks would reside, and other would be the metadata part in which the metadata associated with the blocks would reside. So as it is two-way set associative, let us divide this data part into 2, and per set a row represents set here. So per set there are 2 blocks, so let us represent the 2 blocks as D1 and D2 per set, and associated metadata of this D1 and D2 resides over here in the metadata part. And let's say there are 2 fields, those are maintained. One is valid bit, and let us represent V1 as the valid bit of this block D1, and tag 1 be the tag field of the block D1, and with V2 we represent the valid bit associated with block D2, and tag 2, let it represent the tag field associated with this block D2. Likewise, each of the sets contains 2 blocks, and the metadata associated with each of these blocks resides over this metadata part, right? So after CPU generates an address, first thing that we need to determine is, out of all these sets, which one is the set where the data might reside. So we need to identify the set using this set index part of the CPU address. So there are 16 sets in the cache. So the width of the set index field would be log base to 16, that is equals to 4 bits. That means there would be 4 bits in the set index. Now using the set index to determine the set which is selected is done by that thing is done by set index decoder. So set index decoder is the hardware through which, using the set index bits, we identify the set. So this input from the set index field is applied to this decoder, whose configuration would be 4 cross 16, where 4 is the number of input lines and 16 is the number of output lines. And as there are 16 sets, there are 16 output lines here, one for each of the sets. So this is the hardware, and width of this set index decoder, so this is set index decoder, and width of the set index decoder is same as that of its input lines. So input lines is actually the width of the set index decoder, and that is same as the number of set index bits. So the width of set index decoder is equals to small s, right? So width of this decoder is considered as the input lines of this decoder, and that is equals to 4, and that is same as that of width of the set index field. that is equals to small s. So here we have written it down here. Now after, let's say this set has got selected, and after a set is selected, to determine if that set contains the data, we need to identify if one of these two blocks contains the data or not, and that is done by matching the tag fields of this blocks with the tag field of the CPU address, and that matching, that comparison is done by another set of hardware, that is the comparator. So comparator is the hardware which determines whether the blocks contains the data or not after the set is selected. So here there are two blocks in the set, and to match, to compare the tag fields of this blocks with the tag field of the CPU address, two comparators would be required so that the comparison can be done parallelly. The inputs of this comparator would be the tag fields associated with the blocks and the tag field part of the CPU address. So if the tag fields of any of these blocks is matched, then the output of one of the comparators would be high, would become high. Now one more thing that we need to check before we can say there is a cache hit, that is the valid bits of this blocks. If the tag fields matches and also the valid bit is high, that means the data contained in the block is valid for the process, then only we can say that there is a cache hit. So tag 1 and tag field of the CPU address are matched, and then we are ending with the valid bit of block 1. Here tag 2 and tag field of CPU address are matched, compared, and then we are ending it with valid bit of the second block, that is V2. And if here the output is 1, then only we can say there is a cache hit, right? So what is the width of this comparator? Width of the comparator, as it is comparing two tag numbers, two tag fields, the width of the comparator is same as that of the tag field. That is, it is comparing two numbers which are t bits wide, so the width of the comparator is equals to t. So I have written it here associated with this option. So the comparator is t bits wide. Now if there is a cache hit, that means any of the AND gates output is 1, then we need to pick that particular block which has resulted into a cache hit. So if this is 1, then we need to pick D1. If this is 1, we need to pick D2. And that selection out of this n blocks in the set, that selection is done by using another hardware, that is mux. And the output of the mux is the data from these blocks. So there are two inputs of the mux is the data from the blocks. There are two inputs, as it is two-way set associative. So D1 is one of the inputs and D2 is another of the inputs. And this one of these two blocks, which one has resulted into a cache hit, that would be redirected to output depending upon which one is high, and that can be done by using the selection lines. So what we can do is we can pass this outputs of the AND gates through an encoder, and output of the encoder can be passed as a selection lines to the mux. So if this one is 1 and this one is 0, so this D1 would get selected. If this is 1 and this one is 0, D2 would get selected, right? So the mux, the width of mux is same as that of the number of blocks in the set. So this is same as that of n, number of blocks in the set. So we are done with this. So this is how the data is picked from n-way set associative cache, and we have determined that the width of tag comparator is same as that of the tag field, the width of set index decoder is same as that of the set index field, and the width of way selection multiplexer is same as that of the associativity of the cache. Now if we change, so we are just left with the fourth option, width of processor to main memory, and after the data is selected from here, the data would be passed. So there is one more step, is to determine the word out of this block, the selected block. Let's say D1 has got selected, so within the block there is a particular word which has to be sent to the CPU. So that is determined by using block offset. If there are 4 words within the block, this block offset would be 2 bits wide. That would determine the particular word within the block, and that particular word would be passed to the CPU, and that selection is also done by another multiplexer. Out of the 4 words within the block, within the selected block, one of the words would be selected using a multiplexer, and the selection lines of the multiplexer would be powered by the bits in block offset field. Well, so these are the hardwares in question. So we have drawn only this hardware. Now the thing is, if we change the associativity of the cache, then this would definitely get affected. Width of way selection multiplexer, as it is directly dependent upon n, so this would definitely get affected. So this is out of so this is striked off, because we need to find out which one is not affected. So this one is definitely affected. Now if these two are affected or not, that we need to determine. So let us change the value of associativity, and let us again determine if the width of set index, that is small s and small t, are affected by the change in value of n or not. So let's say now we, keeping all the parameters same as before, now we switch to 4-way set associative cache. 4-way set associative cache. So 4-way set associative means a block would now contain 4 blocks, right? So in all there are 32 blocks, and if now a set contains 4 blocks, then what would happen is that number of set would now be 32 divided by 4, that is equals to 8. So now the number of sets would get reduced to half, that is it would become 8. Now the value of small s is given by log base 2 number of sets. So log base 2, 8 would become 3, right? So the set index would get reduced by 1 bit if we are increasing, if we are doubling the value of n. If you are doubling the value of n, then the set index would reduce by 1 bit. That means definitely the set index is getting affected by changing the value of n, and the set index width, if it is getting affected, that means the width of set index decoder, which is same as that of small s, would also get affected. So this one is also getting affected by associativity of cache. So this is also striked off. Now the width of tag field. Now if block offset, if the block size is kept same, and also overall CPU size is kept same, then this block offset, if the block size is kept same, the block offset would be unaffected. Now by increasing the size of n, the value of n, we have seen that the set index is getting affected. Now the value of t is determined by a minus s minus b. So b is unaffected, a is a constant, and s is getting affected by increase in the value of n, or increase or decrease in the value of n. That means t would also get affected, right? So the tag field would also get, the width of tag field will also get affected by the change in value of n. So this one would also get affected. The value of width of tag comparator would also change depending upon the change in the value of n. So this option would not be correct. So we are remaining with only one option, that is width of processor to main memory data bus. This one is the odd one, and the width of main memory database is no way affected by associativity of the cache. It is determined by the width of CPU or the specification of CPU. If the CPU is 16 bits wide, then usually width of data bus would be also 16 bits. If the CPU is 32 bits wide, then width of data bus would also be 32 bits. So this is not affected by the change in the value of n or associativity of cache. So this would be the correct answer. So thanks for watching. Bye.